Hello folks, let's take a sample IGCSE physics questions, under electromagnetic induction. This is a clear IGCSE question, physics. Well, the problem we have today is to consider, a setup that I have given to us carefully, and then answer some questions that follow. Now, a magnet, so this is the preamble. A magnet is moving towards one end of a solenoid connected to a sensitive center 0 meter. During this movement, the current is induced in a solenoid. So this is the setup with a magnet which is trying to move towards the solenoid. That is a coiled wire. Now the only problem we have is that they say we should come up with 4 possible changes to the system that would increase the induced current. And of course this takes us to electromagnetic induction. But before we can solve this problem, we would have to visit Faraday's law of electromagnetic induction. What does it say? Faraday says that during electromagnetic induction, the induced EMF is equal to the number of turns times the change in magnetic flux, and of course magnetic flux with respect to time. For now, let's neglect Lenz's negative sign. But we could also write that the magnetic flux is equal to the product of the magnetic field, the surface area of the conductor, and then the cosine of the angle between the conductor and the magnetic field. So what can we infer from here? Even though they are asking us to come up with possible changes that would increase the induced current, we realize that during electromagnetic induction, the relative motion between a magnetic field and a coiled wire would establish an induced EMF, and finally an induced current. So should we have any changes that would result in an increase in induced EMF, we would have it also increasing the induced current. So now let's go back to the equation of an induced EMF. Realize that the induced EMF during electromagnetic induction is dependent on the number of turns on the of the wire, the number of coil, the number of turns of the conductor. Would also should you increase the number of turns, you would have a greater magnitude of an induced EMF, and which will reflect in an increased induced current. So we will consider increasing the number of turns. Now we also consider increasing the size of the magnet so that we would produce larger magnetic field or magnetic flux density. So we will also consider the surface area of the wire or the surface area of the conductor. Should you increase the surface area of the conductor, you are in fact increasing the magnitude of the induced current. And then we will also look at the speed for which we move the magnet to and fro towards the solenoid. The faster we move the bar magnet towards the solenoid, the greater the induced EMF, and consequently the greater the induced current. So the 4 possible alterations we could possibly, alteration we can alter to this particular setup is to increase the number of turns. So we have to increase the number of turns. The number of turns on the conductor. We would also have to increase the size of the magnet. If we increase the size of the magnet, we are actually increasing the size of the magnetic field, and hence increasing the magnetic flux, and finally increasing the induced current. Should we increase the size of the magnet, we are increasing the size of the magnetic flux, and of course increasing the magnitude of the induced current. So let's increase the size of the magnet. So we would use bigger magnet or larger magnet, And the third one, I said we should also consider increasing the surface area of the conductor or the wire. So we have to increase, the area, the surface area of the wire. And then finally, we have to increase the speed of the magnet. So in fact, these are the 4 possible alterations we can make to the setup in order to increase the induced current. We have to increase the number of turns. We have to increase the size of the magnet. Now the magnet would have to be relatively bigger in order to get higher or bigger or an increase in induced current. We also have to increase the surface area of the wire in order to get an increase in induced current. We also have to consider moving the magnets relatively faster in order to get an increase in induced current. All right, we could possibly also consider the angle, but for this I think it has already been catered up. It has been placed parallel to the the normal of the conductor. For this, you would say the magnetic flux is at its maximum. All right, so I think that will be all for now. Let's move on to the second part of the question, which takes our mind back to transformers. Now, they're asking us to consider this particular setup and then answer the questions that follow. They say P has 200 turns. P simplify the primary coil. P simplify the primary coil. So the number of turns on the primary coil is 200, and the number of turns on the secondary coil is 800. The EMF induced across the secondary coil is 24 volts. The current in the secondary coil is 0.5 ampere. The transformer operates with 100% efficiency. What does that mean? It means that the transformer, is being able to conserve energy. Energy is conserved, or power is conserved in a transformer. It means there's no heat, there's no loss of energy. For this, we can see the power in a primary coil remains the same throughout the secondary coil. All right, that is what it means if the transformer operates with 100% efficiency. Now the question is asking us to calculate the voltage supplied to the primary coil, and we should calculate the current in the primary coil. All right. So for that, we will need to put down the data that has been given. So from the preamble or from the question, we would realize that the number of turns on the primary coil has been given, which is 200 turns. And the number of turns on the secondary coil has been given as 800 turns. We'd also realize that the EMF, that is the voltage on the secondary coil, has been given as the voltage has been given as 24 volts. And the current on the secondary coil has been given as 0.5 ampere. So it means that they have not given us the voltage on the primary. They have not given us the current on the secondary. Alright. Now, so they say we should calculate the voltage supplied to the primary coil. Now, using the equation of transformer, we can comfortably write that the number of turns on the secondary coil over the number of turns on the primary coil should equal to the voltage on the secondary coil over the voltage on the primary coil. So it means that the voltage on the primary coil could be found as the number of turns on the primary coil times the voltage on the secondary coil divided by the number of turns on the secondary coil. all we need to do is to put in the values. NP is 200, VS is 24 volts, NS, which is the number of turns on the secondary, is 800. Should you do this, you would have the voltage on the primary coil as 6 volts, isn't it? Yes, 6 volts or 6.0 volts. Alright, so let's look at the second part of the question. They're asking us to calculate the current in the primary coil. Now, the number of turns on the secondary coil over the number of turns on the primary coil is equal to the current on the primary coil over the current on the secondary coil. I hope you have not forgotten this formula. Current on a primary coil is going to be the number of turns on the secondary coil times current on the secondary coil divided by the number of turns on the primary coil. So current on the primary coil is going to be NS. NS is 800. IS is 0.5 ampere. And then NP, that is the number of turns on the primary coil, is 200. So the number of current on the primary coil is going to give us 2.0 ampere. I think it is quite easily done. Alright, so I think this is a clear sample of IGC physics, and we have successfully solved it with ease and flexibility. Yes, so that is all for today. So I would like you to share and like, and then give some comments should you have any, and I will gladly attend to any of your comments. Thank you so much for having me. I'd like to see you in my next video. Thank you.